In this video, we will be introduced to the derivative, which is the key idea for calculus. So before we can talk about the derivative, which I've got on that board over there, I want to first talk to you about the concept of the average rate of change from which the derivative will be derived. Okay, so let's consider that we have some sort of function here, this black function f of x, and we want to ask the question, what is the average rate of change between 2 points on the graph of this function? Okay, so let's say the 2 points are x is equal to a and x is equal to b. So sometimes this question is posed as what is the average rate of change on the interval a to b. Alright, so here's x is equal to a, and here's f of a, which is the point on the graph. Here's x is equal to b, and here's f of b, which is that point on the graph. And the average rate of change over that interval is going to be the slope of what we call the secant line. The secant line is this blue line that I've drawn that connects the 2 points. Alright? So as we move from x is equal to a to x is equal to b, the function increases from here to here. Now as you can see, this function's curvy. It doesn't increase linearly. But when I take these 2 points and I define the unique line that connects just those 2 points on the graph, that is a line. And the slope or the steepness of that blue line is going to describe on average how fast the function is changing. Actually, inside this interval, the function changes differently at different times. For example, if you look at this, it's kind of changing slower here, and then it's ramping up faster and faster. But we just want the average. That's why it's called the average rate of change. Okay, so in order to get the average, we'll just draw a line between those 2 points, and then we'll just calculate its slope in the normal manner. Remember that the equation for slope is going to be the difference in the rise over the difference in the run. Okay, so the 2 rises are f of a and f of b. The difference on the top is the difference in the rise, f of b minus f of a. And then the difference in the run is how fast I went, how much I went over there, so that's b minus a. Okay, so this fraction is going to give us the slope of the blue line, and that's what we would call the average rate of change. Alright, so now let's get into the key idea of calculus. What calculus does is seek to describe how a function is changing just at one instant. Not so much how much is it changing on average between 2 points, but let's say that I just wanted to talk about the one single point, a. X is equal to a, and there's the y, f of a. Alright, how fast is the function changing exactly at that time? Well, usually for this trick over here, I would need 2 points so I could connect the line between 2 points. So for the concept of derivative, what we're going to do is first we're going to define the point A, then we're going to define the point A plus H, which is a point that's very, very close to A. This is where the limits come in. Okay? So what we're going to do is we're going to take the point of interest, and then we're going to move to the right just a little bit, which is to say we're going to move over a distance h. Now over on this board, the distance that we moved over was a minus b, so that's why you have the b minus a over here. And the distance between the point A and the neighboring point a plus h will just be the small distance that I moved over h. So instead of calling this point b, I'm just going to refer to it as a plus h, because I moved over a little bit h. Alright? Then, if I did that, I would be able to, just like over here, draw a blue line that represents the secant line that connects these 2 points. So I could just take my blue marker here, and I could draw a line that connects those 2 points. However, if these are 2 distinctly different points, then this is still just an average rate of change because it's a line connecting 2 different points. For a derivative, what we want to do is take these 2 points, actually take this point a plus h and move it closer and closer and closer to the point A until these 2 become one and the same point. Okay? So what we're going to do is decrease the distance that separates these 2 distinct points, which is to say we want to take the limit as h goes to 0. Okay, because as h goes to 0, it gets closer and closer and closer to the point A, and then those 2 things merge into just one point. Now what happens to the blue line when I take those 2 distinct points and merge them just into one point? what happens is before what we were calling the secant line is now going to be called the tangent line. The word tangent means it's just touching. And the thing about a tangent line is a tangent line touches the graph only at one point. It doesn't connect two separate points on a graph like a secant line. It just touches the graph at one single point. And if we could figure out what the slope of that line is, of that tangent line is, that would describe for us the instantaneous rate of change, because that's how fast the function is moving just at that one single point. Okay? So what we're going to do is we're going to take this definition of the slope, difference in the rise over difference in the run, and we're going to write it right here as we've defined the 2 points, a plus h. You see how the a plus h there replaces the b right there? And then we're going to subtract off the f of a, just like we did over here. And then on the bottom, we're going to take the a plus h, which again is the same conceptual thing as the b here, and we're going to subtract off the h. Now you can see here, actually, if I do a plus h minus a, that would simplify a little bit. I could really just cancel the a's there because I have a plus a and a minus a, and I could just have an h there. Okay? But that's where the h comes from, is that it's the difference between these 2 points. Alright, but like I said, for the concept of calculus, we want a tangent line. We just want to be touching the graph at one single point. So we're going to get the secondary point and move it closer and closer and closer to the original point. And that's why we're taking the limit as h tends towards 0. This is the limit as this little bit h that differentiates them gets smaller and smaller and smaller just until it disappears. Okay? So this is actually what they call the limit definition of the derivative, and I'll show you how to work with that next. So this is what's known as the derivative, and it represents the slope of the tangent line. Okay, what is instantaneous rate of change versus average rate of change? Let me give you a little concrete real-life example of that. Let's say you're driving in your car, and maybe you're driving from Seattle down to Portland. Okay, so let's say, I don't really know how far it is, but let's say it's 200 miles away and it takes you 4 hours to get there. Well, that kind of took a long time, right? Now, if it took you 4 hours to drive 200 miles, how fast were you driving? 200 divided by 4, 50 miles an hour. So that tells me that I was driving 50 miles an hour. Now, if I said I was driving 50 miles an hour the whole time, that would be an average rate of change, because I would say my average speed is 50 miles an hour from the minute I leave my house to the minute that I get to my destination. However, if you've ever been on a road trip, you know that's not true, because the reason your average was 50 is usually you're probably going about 65 or 70, but then you stop for gas, you stop for lunch, stop to take a picture, go on a hike or something. That's why it took you so long, right? So the instantaneous rate of change is the speed that it says on your speedometer. When you're driving, right now I'm going 70 miles an hour, then I had to slow down for traffic, now I'm going 45 miles an hour, etc. The speed measurement on your speedometer is always changing. It changes every minute, and it represents exactly how fast you're going at one moment in time. That's what the derivative is. It describes how fast our function is changing just at the one moment in time. And you can see how sometimes that would be more useful and more descriptive than just an average rate of change, which is to say I drove from here to there and I was driving 50 miles an hour the whole time. That's not true, but it just gives me an average. Okay, so now let's move on to some business concepts that will have to do with this. So let's say maybe we're going to have a cost function that describes what is our total cost to produce X units. Okay, so that's a familiar function. C of X is going to be the total cost in dollars. And let's say that X is going to be the number of units produced. And what we're going to do here is we're going to calculate an average rate of change, and then we're going to compare it with the instantaneous rate of change, which we will derive using the limit definition of the derivative. Okay, so let's say that we have a concrete model of $100 in fixed cost, and then we have some variable cost over here plus x squared. So if I'm not producing any units at all, I still have a fixed cost of $100, but when I am producing some, it's going to cost me more and more. Might as well take a graph of this. Keep in mind, a graph is very useful for a lot of different cases. And you can see that this is going to be a parabola, which starts when x equals 0 at $100 and then increases in its parabolic form. And notice that I have not drawn it for negative x because when we're talking about an application, in this application, it doesn't make sense to produce negative units. So I'm only drawing it in the domain here from 0 to infinity, including 0. Okay, so let's ask the question, what would the average rate of change be between, let's say, 2 points, x is equal to 1 and x is equal to 3? Okay, so why don't you guys calculate the average ROC, that's the abbreviation for rate of change, and I'll write over the interval from 1 to 3. Okay, so using the definition that I showed on this board before I erased it there, why don't you go ahead and calculate what the average rate of change is. Alright, and so what we're looking at here is there's 2 points, 1, and the height at 1 is going to be 1 plus 1 squared, so that's 101. And then the other point is 3, and the height will be 100 plus 3 squared, which is 9, so that's 109. Okay, and just calculating the average rate of change is just doing the rise over run, right? So it's the difference in the two rises, so 109 minus 101, divided by the difference in the run, so that's going to be 3 minus 1, so that looks like it's 8 over 2, so that's equal to 4. Did you get 4 for your answer? I hope you're taking a moment to try these yourself, even though it's pretty early on. You definitely want to get the practice. Okay, before I go any further, I'm going to ask a little deeper. 4 is the answer I got. For what? You can see that in this application problem, I've given you a couple units to work with. The x is in the number of units produced. The y is in the dollars. So this is for what? What is the unit on this slope? See if you can answer that question. The answer is for what? Alright, so in order to answer this question, what we want to do is consider what is the unit on the top and what is the unit on the bottom. You can see what we just calculated for this 4 is this is a ratio. So it's no surprise that the unit here for the answer 4 is going to be a ratio. And on top, these were both in units of dollars. Right? So this is actually $8 on the top. So on the top it's going to be dollars. And on the bottom, these were number of units. So divide by number of units. Alright, so kind of double using the word units here, but here I mean the number of units produced. And what the average rate of change represents is between the production level of 1 unit and 3 units, the average rate of change is $4 per unit. Okay, so that means on average, if I go from 1 to increase to make 2 units, it'll cost me $4 more. And if I go to 2 and increase to make 3 units, it'll cost me $4 more. It's costing me $4 per additional unit that I produce. Okay? But remember, that's just an average rate of change like the 50 miles per hour in the car, and it's probably not going to be that same exact increase depending on your production level. So the next thing I'd like to do is calculate the instantaneous rate of change using the definition of the derivative. And I'll show you how this works. Okay? So let's see, the derivative, which actually I forgot to introduce this, but it's called f prime of x. Okay, this will be what it's called the derivative of f with respect to x. Alright, it's represented by f with a little prime there, call that prime of x. Alright? So this is going to be from the limit definition, the limit as h tends towards 0 of f of x plus h minus f of x divided by, and really on the bottom here we have x plus h minus x, but you can see that the positive x and the minus x cancel out, so really on the bottom all we're left with is just the letter h. Alright, so this is a little bit different from what I showed before. Sorry, I don't think you can see that because of the glare. So let me rewrite it a little lower. Alright, so before I had the letter A where I now have the letter X, And that's just a little bit of a technicality. Because I have a function of x over here, I would like to calculate and describe the instantaneous rate of change for all points. Not just for one specific point like the number 1 or 3, but no matter what the x is, I would like to have a description for the derivative. So that's why I replace the letter a, which usually represents just one single real number, with the letter x that represents a variable, and then I can plug in different values of a that I would like. Okay? So anyway, besides that, the limit definition has not changed a bit, and all I want to do now is kind of a plug and chug type of thing, where I take the definition here. Oh, sorry, it's not called f, it's called c. Here, this is our cost function c. And now I'm just going to replace with what I know about the function c. c of x is 100 plus x squared. Okay, so let me do some replacement here. The limit as h tends towards 0, c of x plus h. That means that I'm going to take my function c, and wherever I see the letter x, I will replace it in parentheses with x plus h. So my function c is 100 plus x squared, but c of x plus h is 100 plus x plus h squared. Okay, so all I did here was replace the independent variable x here with the quantity x plus h. Now I'm going to continue with the instructions, which tells me to subtract off c. And notice my use of parentheses here, kind of like when you're doing the profit, when you're taking revenue minus cost and getting profit out of it. You want to make sure you have an outer parentheses when you have more than one term, because a negative sign is going to factor through. Okay, so I put the open parentheses, and c of x is just exactly what it says there. So I'll just copy that down. And then the whole thing is just divided by h, which I've already simplified, and is the distance between the point x and the neighboring point x plus h. Okay, whenever I take a limit, my very first step is that I will just try to plug in the limiting value and kind of see what happens, okay? So let me just plug in 0 here and just do a quick innocent plug and chug, okay? Let's see, if I replaced... Keep in mind, this is a little different than the other limits you are doing. The limiting variable is h, not x. Okay? So in this problem here, I'm going to replace all the h's with 0, but not the x. Be very careful with that. So 100 plus x plus 0 squared. So x plus 0 squared is just x squared, minus the original 100 plus x squared. Divide it by the h, which I'm now going to replace with a 0. Maybe it's a little more clear if I write it like this. Okay, so what I've done for plug and chug is I've just replaced the value, wherever I see an h, I've placed it with the value 0 here. And what happens when you just innocently do that and you kind of look at it, the first thing you may notice is, red alert, I'm dividing by 0, so that's not going to be good. And then I wonder what I got on the top here. Can you guys see how this is going to cancel out on the top? Yeah, you just get 0 on the top here. So what you end up getting is 0 over 0, and that's our familiar indeterminate form. Okay, that's the indeterminate form. That's why that was so important from the concepts of limits before, is because this is going to happen all the time when we approach the calculation of the derivative using the limit definition. Whenever you do that and you plug in, especially since you have an h on the bottom there and the h is going to 0, you're going to get a divide by 0. But because this derivative is not going to be infinite and it's actually going to turn out to be a real number, you must also get a 0 on the top so that you get indeterminate form as opposed to does not exist, that represents the vertical asymptote or blow-up behavior. Okay, so I have to do a little more detail here. I'll have to do a little more investigation. And just like before, I think my next step will be maybe to go back to the beginning and factor it out. Maybe if I factor it out and cancel some things, then I'll get something a little different this time. So I'm going to go back to this stage right here, and instead of just plug and chug and plugging in the h is equal to 0, I'm actually going to FOIL this out, and then I'm going to try to cancel some terms. Okay? So that's what you got to do there. FOIL out and cancel terms. Alright, and so instead of that, I'm going to write the limit as h tends towards 0 of 100 plus x squared plus 2xh plus h squared, and that's minus 100 minus plus x squared, and that's still all divided by h. You know what I would really hope to get out of this? Is I would hope that when I do all this algebra, I don't have a divide by 0 anymore. That would really be great, because then I wouldn't have this messed up divide by 0. Okay, so my goal right now is to try to simplify the top as much as I can so that I could cancel a factor of h with each term on the top and hopefully eliminate the problematic divide by 0. That's what I'm going for. Okay, so let's see what I got here. 100 minus 100. Cancel, cancel. And remember, this is going to be a minus x squared because the minus factors through. So positive x squared minus x squared. Cancel, cancel. Okay, so the next thing that I'm going to have is the limit as h tends towards 0 of 2xh plus h squared divided by h. Remember, it would be great if I could get rid of that pesky divide by 0 on the bottom. Can you guys see a common factor of h in both of the terms on the top? That's why factoring is so important when we do this math here. There's an h here, there's an h there, so I'm going to rewrite the numerator with one of the h's taken out. And on the inside, 2x plus h to the first power. Okay, now if you don't believe me, you can refoil it out and see that I've got the same thing on the top, but keep in mind that you're going to want to have the skill of being able to just mentally extract the power of h there, because that's how we're going to get rid of the divide by 0 on the bottom. Remember, in the concept of a limit, although the h is tending towards 0, it never is strictly 0. It's everything but 0. It's tiny, teeny, tiny quantities that are close to 0, but it's not 0 itself, so that's why I can cancel it out in the limiting sense. And then what I get to is the limit as h tends towards 0 of what's left on the top there. And now I can plug and chug, and so I'll just plug in h is equal to 0, and I will get 2x. There's 2x plus h, 2x plus 0, 2x. Alright, so this is what I'm going to say is the derivative of c, which I call c prime. So I can say that c prime is equal to now, not this limit, all this stuff. We did all that work to get that. By the way, after this lecture and future lectures, I'll be giving you a lot more easy ways to calculate a derivative. This is not the general method that you will be using to calculate derivatives, okay? But it is important for the lesson to see where it comes from. So it took us all that work, but turns out we got the answer is the derivative of c is equal to 2x, all right? This is the instantaneous rate of change of the cost function with respect to the number of items produced. And just like the average rate of change, it's going to have the same exact units because it's derived as a ratio. It's derived as a slope calculation where the difference in the y's is on the top and the difference in the x's is on the bottom. So the units on this is going to be dollars, which is the y unit, per units produced, because that's the x unit. So I'll just write units produced so you don't confuse it with the concept of units, okay? So c prime of x is equal to 2x, and the units on that is dollars per units produced. All right? Now before, remember we calculated the average rate of change over the interval from 1 to 3. That was $4 per unit produced. Okay, that was $4 per unit, which is to say, on average, every time I decide to make one more unit, it's going to cost me $4 more. But that's an average concept, and really now I can get the instantaneous concept, which is to say, what if I'm exactly producing one unit? How much would it cost me to make one unit more? What if I'm making 2 or 3 or 4 or 5 or 6 units? This is exactly how much it will cost me to produce one more just at that instant, at that exact specific production level. Okay, so now let's just evaluate that and kind of compare them. What is c prime of 1? What is c prime of 3? These are the two endpoints that buffer the average rate of change, the interval right there. Let's see, c prime of 1, That's equal to 2 times 1, so that's $2 per unit. Okay, what is C prime of 3? That's 2 times 3, so that's $6 per unit. So now I kind of see the difference between the concept of the average rate of change and the instantaneous rate of change. On average, over the interval from 1 to 3 units, it was average $4 per unit. But really what's going on here is that if I'm at the production level of 1 unit and I want to increase by 1, I will have to pay $2 more. If I'm at the production level of 3 units and I increase by 1, I will have to pay $6 more. Now coincidentally, we see that the average between 2 and 6 is 4, and that's like, that's how we got the average rate of change. But the instantaneous rate of change is more important because just like how your speedometer tells you what your speed is right at that moment, this is going to tell you how much more it will cost you to increase your production level by 1 right at the moment when you're making 1 thing or making 3 things or whatever have you. Okay, great. So that is going to be our main application. It's going to be for total cost, revenue, and profit functions. But I just want to go into a little visualization to end this video of the difference between what does it mean to be differentiable versus what does it mean to be continuous. Okay, so we talked about continuity a little bit before, and we already said that in a continuous function, that's a kind of function that you can draw without taking your pen off the page. Okay, now we're going to talk about what it means to be what we call differentiable. Differentiable functions have a derivative that exists. Okay, so if I say that a function is differentiable, it means that the derivative of the function exists. So the derivative of f of x exists. Alright, let's take a picture and compare that versus continuity. Continuous functions. Alright, so before when I was drawing you a function to make an example of continuity, let's see, maybe I had a function like this. I really had a couple different things that I was considering were maybe problem points for me. And I've highlighted them here on the values x is equal to 1 and x is equal to 2. X is equal to 1 was a sharp corner. Do you remember if this sharp corner is continuous or not? It was continuous, right? Because the function value exists, the limit as we approach the function exists, and the limit is equal to the function value. And more than that, I can draw the function without taking my pen off the page. Okay, so x equals 1 is a point of continuity. The function is continuous here. Was the function continuous here at x is equal to 2? No, it's not, right? Although the function exists, the two one-sided limits disagree, and so by the continuity checklist, we cannot have continuity at that point. Alright, so what I'll tell you now is that for differentiable functions, the derivative of f of x exists. In order to visualize that, I have to go back to the concept of a tangent line. A tangent line is a line that I can draw that touches just one single point on my function. It does not touch any other points on my function, and the key thing is it is uniquely defined, which is to say that there's one exact line just like that I can draw. And there better be one exact line that it's just like that I can draw, because the slope of that line will be the derivative, right? So let's consider this point over here. Right here, if I want to draw the tangent line to this point, I can just draw one line that's just tangent. It's just touching that point. It doesn't touch any other points, and it is the one single unique line that's just tangent to that point of the function. Now let's go to this part right here, which is a non-continuous point. Do you think the tangent line exists here? Do you think for this function value, f of 2 right here, I can draw one line that's just tangent right to that function, but it's not touching any other points? It's actually impossible. There's no way that I can draw this because I kind of want to draw it, but the function makes such a crazy jump there that I'm not going to be able to draw it. Okay, the other thing is if I had the limit definition still up, if I tried to calculate that limit, similar to how these two one-sided limits do not agree, that full overall limit, that is the definition of the derivative, would not be defined because the two one-sided limits would disagree. Okay, so if a point is not continuous, therefore it is not differentiable. Okay, if f of a is not continuous, then it is not differentiable. Alright, differentiable. I'll just call it diff because I don't have enough room right here. Alright, so this is one way right here to figure out if something is differentiable or not. If you know it's not continuous, forget about it. It's not going to be differentiable. That's an easy way to figure that out. The only other type of point that we'll have to consider is this corner type of point right here. Alright, this is a continuous point. However, do you think, similar to this point over here, that I can draw one unique line that just touches this point, but it doesn't touch any other points? Well, sure, I can draw this line right here. Look, that touches that point, but it doesn't touch any other points. Okay, so then you would think it's differentiable, but the key idea was that the tangent line must be unique. It must be that there's only one tangent line that I can draw. However, at this corner, it's so sharp, it changes so quickly, that I could also draw this tangent line. And another thing, I could also draw that for a tangent line. I could also draw that for a tangent line. You see what I'm saying here? There's too many tangent lines, okay? So it's different than when a point's not continuous, you can't draw a tangent line because it's impossible because of the discontinuity. However, when a function is continuous but it has a sharp corner, you can't draw the tangent line, not because you can't draw one at all, but because there's too many to draw. It is not uniquely defined at a corner. Okay? So that's the one time at which a function can be continuous, but it's not differentiable. Actually, there's another thing we'll see later, the other ways that it can be continuous but not differentiable. But the lesson here is that at sharp corners, that's because the corner was so sharp. At sharp corners, a function is continuous but not differentiable. Okay. Remember, the key thing that you want to learn from this, the takeaway from this lecture, is that the derivative represents the rate of change of a function at exactly one instant, at one point for x. Okay? And if I have some point that, well, it's going down, and then it starts to go up, it just totally changes its mind in a sharp corner, I cannot say exactly what the one unique instantaneous rate of change is. So therefore, it won't be differentiable. Alright, one more thing that we want to talk about that's along that same vein is what is the sign of the derivative for different parts of a function. Okay, so let me draw you one more function. And this time I'll make it a nice function. I'm not going to do any tricks, no corners or anything here. This function is continuous because I drew it without taking my pen off the page. It's also differentiable everywhere because it's continuous and I don't see any sharp corners here. And now what I want to do is I want to discuss what is the sign of the derivative. And by sign I mean, is it positive or negative? What is the sign of the derivative? The derivative again represents the instantaneous rate of change. Okay? Now, let's try to picture the tangent line. Picturing the tangent line is really going to help you to answer the question of what is the sign, because if a line is going up, its slope is positive. If a line is going down, its slope is negative. So that's what I mean by the sign. Okay, so let's start over here. Can you picture a tangent line to the function, let's say at the point x equals 0? Try to draw it on your own page. See if you get it. Yeah, the tangent line looks something like this. It's just touching that one point. It's not touching any of the other points around. And what's more, this is a line with what kind of slope, positive or negative? It's a positive slope, that's right. So that means that at this point right here, f prime is greater than 0. The sign of the derivative is greater than 0, it's positive. Okay, let's pick another point over here. Let's say maybe in another color. Let's pick this point right here, I'll call it A. Try to draw the tangent line at that point A. It's a little tricky because it looks so much like a line already, the function itself, but tangent line kind of looks something like that, right? And to answer the question, what is the sign? Well, that line is going down, right? So that means that the derivative f prime is less than 0 when the line's going down. It turns out the function's also going down. Think about this for a minute. Think about if I had a little ball and I was rolling the ball. At this point, the ball is rolling down the hill, right? It's going down. This is what we call decreasing. The function is decreasing at this point, and whenever a function is decreasing, its derivative is negative. Okay, now if the ball is right here, I would actually have to be doing some work to push it up the hill. And right here, this is what we call increasing. The function is increasing, and so we would expect the derivative, which is the rate of change of the function, to be positive, because the function is going up, so it's changing in a positive way. Here, the function is going down, so it's changing in a negative way. Okay, so now that we've determined that, we can kind of separate this function into different regions. Let's try to mark the places where the derivative is positive and the places where the derivative is negative. See if you can mark off the different regions where that's true. Okay, so keep in mind, whenever the function's going up, whenever the function's increasing, the derivative is positive. So it looks like the function's increasing and it's increasing, and then it gets to this peak right here. That's when it stops increasing. Okay? Then it's decreasing and it's decreasing, and then it gets to this trough right here. And at the very bottom of the trough, that's when it stops decreasing. And it begins increasing again. It goes up and up until we get to this peak right here. And that peak signals when it changes from increasing to start decreasing again. Okay, so we've got all different regions here, and we would expect that in this type of region, whenever the function is increasing, the derivative will be positive. So let me write that down. When f of x is increasing, we will say the derivative, f prime of x, is greater than 0. And that's happening here, and it's also happening over here. So I think f prime of x is greater than 0 here too, because the function's increasing. Okay? And likewise, whenever the function is going down, that means that the slope of the tangent line will be negative. The behavior of the function is that its rate of change is negative. It's changing in the negative direction. It's going down. So here's where f prime of x, we would expect it to be less than 0, and we're going to call that decreasing. Okay, so in this region right here, increasing, decreasing, increasing, and here again, f prime of x less than 0 is decreasing. All right. Now there's a few special places I claim on this picture where the function is neither increasing nor decreasing. And I wonder if you can find those spots and tell me what's the sign of the derivative at those special spots. I see 3 special spots. Can you see them? Actually, they coincide exactly with where I've drawn these dotted lines. At the very top of the peak right here, at the very bottom of the trough right here, and at the top of the peak right here, what can I say when I'm at the top of the mountain? I'm not going up anymore because I got to the top, but I'm not going down anymore because I'm chilling at the top. So this peak right here has a derivative that's exactly equal to 0. 0 is the only real number that I can say is not less than 0, nor is it greater than 0, because it's equal to 0. It doesn't have a positive sign, it doesn't have a negative sign, it's equal to 0. And these special spots are going to be very important as we move along. This is really one of the key things that calculus can do for you, is that if you have a mathematical form that describes something of interest, I can tell you where all the peaks are, and I can tell you where all the troughs are. We will call these later the optimal values of the function, and at each one of those points, the derivative is going to be equal to 0, if the derivative exists. Okay, so here f prime is equal to 0, and right here f prime is equal to 0. These are very special spots. Whenever your function hits a top peak, whenever your function hits its lowest bottoming out point like this, the rate of change stops for a minute and it hits 0. And that's because, like for instance over here, the rate of change f prime was negative, and then it turned to be positive. Well, how can a number change from negative to positive? It has to go through 0. Think about the number line. The only way to get a negative number to change into a positive number is for it to go through 0. Okay? And if we consider what the tangent line looks like at a point like this, it's going to look just like this, which is a horizontal line. And do you know what the slope on a horizontal line is? It's 0, exactly. So that's why the slope here, 0, says f prime is 0, because the derivative is the slope of the tangent line. Okay.